Thank you very much. And thanks to the organizers for putting this together. What I want to talk to you about today are assessments and how they're driving what the students are doing in the classroom. I want to start with the assessments, and then once we understand what we can learn from those assessments, talk about how you put a curriculum together and individual lessons and give you a simple example at the end. All right, so to begin with, let's go to the classroom at Berkeley. All right, you all recognize it. All the seats are facing forward. That would be me up here, sage on the stage, talking at the students. By the way, this has worked really well for the monks. Before the printing press, you know, you read the book, and the monks sat and copied all the things that were said, and you had extra copies of books. Worked for the British Empire. You know, when you were trying to be a global power, you needed people who could be local authorities who would be confined to doing what you wanted them to do. It was really efficient and really effective. Question is, what is it doing in this day and age? And then, when you walk out of that lecture hall and you walk into legacy chemistry exams of this ilk, which of the following sets of quantum numbers, N, L, M sub L, M sub S, who knows what those are, describe the valence electron of highest energy in a ground state? This is walking out of a general chemistry class. Now, I know there's a few quantum chemists in the room. I love quantum mechanics. But I particularly appreciate about quantum mechanics not this, which most of you, if you don't do quantum mechanics, never use. What I particularly appreciate about it is the colors. We wouldn't have colors. The world would be black or white if it weren't for the way that light interacts with matter. Isn't that cool? And that I can design experiments to understand matter based on that idea? But that's not what That's not what the students were asked. This is actually real legacy chemistry exam questions from not that long ago, and I would argue that they're even being asked today. When a solution of sodium chloride is vaporized in a flame, the color of the flame is. Oh, you know, I can memorize that. A molecule or an ion is classified as a Lewis acid. Well, yes, it's very important to know Lewis. He was, after all, for 46 years, the dean of the College of Chemistry at Berkeley. And now I get into all these words. Protons, sorry, there's a misspelling there. Electrons, bonds, resonant loop, oh my goodness. All right, so where are we at this point in terms of what the students are really getting out of this? And I'd argue that students that we select out that are good at memorizing, you know what? They do really well in those exams. So this is a question for you. What do these kinds of legacy exams diagnose? A, that students have good memories. What do you think? Boy, we have selected out at Berkeley these super memorizers. They know every single word that I have ever uttered because they watch my videos several times and memorize it. They have good memories. Students will do what is asked of them, right? So the students who buy in that they're going to be chemists, that they're going to be doctors, they'll do whatever you ask them to do, but what are they learning? Teachers are a good delivery system. Well, pretty effective if all you want them to do is memorize. And this is one of my favorites. Teachers ask questions that students can answer. And everyone feels good. All right. If you don't assess what's important, what is assessed becomes important. Okay? So let's think about this. So what I want to tell you about today is how we can change this. And I love Sir Ken Robinson. If you haven't listened to any of his TED Talks, they're really quite fun. His description of what we're doing in these classrooms, including high school classrooms, is hours of low-grade clerical work. And that is, and the students who buy into that, they do quite well with that. And then we wonder why students can't sit still and focus. And so the question is really, what can we do that's different? And I know that I'm always optimistic, even in the face of things that when you shouldn't be optimistic, but I am optimistic right now because there is a climate of possibility, starting first with the next generation science standards that are talking about science practices and cross-cutting content and core ideas. The College Board is redesigning the advanced placement program. The biology test was out for the first time. Next year, it's going to be the chemistry test, and it's going to look different. You know, I always have dreams of it being way over here. Well, it's moved from where it was, and it will ask for a lot more understanding as opposed to memorization. And then we heard earlier today about the MCAT, which has developed new themes and is coming out. So I'm optimistic that there's a movement afoot to start to change these assessments. I might point out here that, do you see higher ed anywhere in that? Not really. We have these wonderful reports, the two of them that I've listed up here, Assessing 21st Century Skills, and the Discipline-Based Education report that Tom referred to that we talked about earlier, that are also pushing for a different outcome, a different type of diagnosis, a different hope and dream for the students that come through our classrooms. And I have Ken Robinson up here again. Human intelligence is richer and more dynamic than we have been led to believe by formal education. We now know from neuroscience that everybody can learn, that the brain is malleable. It's not a fixed intelligence, as many of our students have been led to believe when they get into our classroom. Okay, so what I want to summarize this work with is that we can redesign what we're doing in our classroom based on this research, and I would argue that we want to build in science practices. We do want to make these connections, as we've heard about today from other talks, with an ultimate goal to allow students to learn the knowledge and skills that they can then apply to new situations. Okay? So let me tell you about the experiment. I want to skip this slide. The experiment that we've done at Berkeley. All right, so in Chem 1A, we started to write the exams differently. I'll show you some examples. Let me try to, in a nutshell, explain what those exams look like. If you saw the answer as a student in the class, you'd go, oh, I knew that. Okay? But because it's a new question that you have never seen before, you can't memorize it. You actually have to understand something that actually I would have thought all the students did understand in order to apply it to this near transfer, this new situation, this problem that you couldn't have memorized. All right, so the students knew that this is what we were doing, and in order to understand their perspective more, since they were doing most of their learning where? Not sitting in my classroom. They're spending hours outside of the classroom. So we also wanted to know what were they doing to prepare for these exams outside of the classroom. So we interviewed them 3 times, and pretty amazing amount of work because we ended up having about 70 students that were interviewed 3 times in the semester. After the first exam, between the second and third, and this should say right before the final. All right? And we wanted to know how were they using resources when they were directing themselves, and then did they change their study strategies and what caused them to do that? Okay? So we were able, based on the interview data, so coding the videos, to classify the students into 4 groups. So the lowest group here, I call them, they're gathering facts. What's the answer? That's all they want to know. And in fact, these students will actually tell you that they did not practice the 6 midterms exams from previous years. Why? Because those questions weren't on their exam. And they are totally confused by not doing well. They're shocked by their grade because, after all, they put a lot of time in. All right? Then we go to the next group, which I would call are a little bit higher. They're still fairly passive, but they're learning procedures. They're starting to understand that they don't quite get everything, and they're trying to make small connections, but they're largely, the authority for the information is external to them. So these two groups are both external, is where the authority lies. Then we get to this group that are confirming their understanding. So they're taking information in, and they're beginning to really get serious about trying to evaluate it. Do I believe it? Is it right? Let me check this other source. They're asking other people. They're trying to give explanations, and they'll come to you and they'll say, am I thinking about this correctly? So they'll tell you what they've already thought about. And this final group is pretty amazing. They're thinking about chemistry all the time, and they're trying to figure out where it applies. Okay, so our bright, motivated, talented students that come to Berkeley, where do you think they are? They're not, they're somewhere number one. Fortunately, there's quite a number in number two, but that's where they are. And they're super memorizers. And so here's the distribution of the students that we interviewed over those 3 time periods. So this is time period 1, 2, 3. And then this is the ones that are in level 1, level 2, level 3, level 4. So the majority of our students, highly motivated students, are really looking for procedures. And what this shows, though, is that the number in level 1 actually decreases over time. The number in level 2 finally decreases. By the way, it doesn't decrease so quickly because the first exam's a fluke. Then it's the second exam, it's like, holy crap, she's serious about this. And then, because they're highly motivated, they actually do start to use better approaches. But it's not as many as you would like. Now, this coding scheme, because we did it very systematically, we used a lot of information, how they were using the text-based resources, how they were using study groups, how they were using problem sets and whatnot, and it was coded by 2 different coders to validate the coding, does correlate very well with the mean percentile on the exam. So this is exam 1, exam 2, this is level 1, level 2, level 3, level 4, and each of these is a different one of the exams. So if you were coded as level 1, sure enough, you were in the 30th percentile in the class. If you're coded as number 2, you're around 50th, level 3, level 4. So this is really good correlation. So these exams really were pushing these students to achieve, to think, to study differently, all right? Okay, so what we found then is that the students came in as fairly passive learners. They stayed focused on reading the text, and they weren't very reflective when studying. And those students who remained this way, they didn't improve through the semester. But those who became more active learners, who were looking more deeply at the content, they moved away from just reading the book. They started to work with peers. They began to ask more questions. And this goes way back to a study in 1984 about surface level and deep level approaches, which have been studied in the classroom context. And this is the first time that we're addressing it. What are students doing when they can choose how to digest the material? And then this we still have to do more work to prove, but what prompted the changes in strategy were that the questions were asked that made them apply what they were learning, and they could not memorize an algorithm to solve the exam question. So the assessments drive the behavior, which drives the learning. So my argument is that we really need to think differently about how we ask these assessments. Now, let me say, I'm at Berkeley. I've got 1,300 students in this class, and I've got a limited number of graders. So there are a lot of multiple choice questions here. There's some open-ended ones, too. The trick is, can we start to learn how to write better multiple choice questions? And then in addition, in multiple choice, I actually have some answers where I give partial credit because they're not bad. You can select that one, it's okay, but it's not the right answer. It's not the best answer, I should say, rather than right answer. All right, so now what I want to kind of pull together for you now is looking at the kinds of ways that you can bring data in to write an exam question. Okay? We heard earlier that if you learn about carbon, a single atom, and then that's all you learn about, and then you look at the next problem, that's all you learn about. Actually, scientists and humans in general are really good at looking at patterns and trying to understand those patterns. So a lot of our exam questions bring in data, patterns, that students can look at, and I can ask lots and lots of questions here. This is kind of a simple, very chemistry-related one where we're just looking at the elements going across the periodic table combined with hydrogen. And I can ask, wait a minute, how do you explain that these are solids? What's the bonding? How can you, would you expect these solids to have an odor? Why are these gases which dissolve in water? What are the numbers? Why do they go 1, 2, and then get strange, and then 3, then 4, 3, 2, 1? Why do I switch it around? Why is the hydrogen first here and the hydrogen second there? So you can really start to ask a lot of questions, a lot of why questions to get the students thinking. Here's one where I have two solutions, 100 milliliters of each. They're both acids. They are both pH 3.5. But boy, do they look really different. So if I put a piece of metal in them, is it going to react differently? They're both 3.5. Am I going to need the same amount of sodium hydroxide to neutralize those two solutions? What makes them both 3.5? Why are they called acids when it looks like you know, there's a whole lot more stuff in this one? So we get them. We really are trying to connect the macroscopic properties with this atomic level view. Here's a fun one. This is vanillin, eugenol, zingerone, capsaicin. I actually gave this one just before the pepper spray incident at UC San Diego, if any of you remember that. But again, look at the data. Look at how interesting it is. There's rings in each of these. They have the same substituents. They have long chains hanging off of them that are different lengths. Look at what happens to the melting point. Look at what happens to the boiling points and the solubilities. And why in the world can I smell vanillin so well? I can't smell capsaicin, but gosh, when it gets into my mouth, it doesn't go away. Why is that? So that would be a question that we'd ask, and we'd expect that they could take the data and start to understand it. All right, so if we're driving towards exams that bring in data and observations and getting the students to think and asking questions where they have to use intermolecular attractions in this case, or hydrogen bonding, and what is a boiling point, get them to use that to explain data, what would we do in the classroom to build their expertise in this? Because they don't come in with expertise at looking at tables like this. By the way, a hidden thing in many of these tables is that there's a control of variables. And our undergraduates are not really good at understanding which variables are being controlled. And we spend a lot of time comparing things in which I say, I can't compare those two because you're changing two things. So what we've done in order to build a curriculum around this is to build around core ideas in chemistry. What are the main things that we want the students to know? And I want to point out that the Next Generation Science Standards is doing this, AP Chemistry Redesign is doing this, and MCAT has a really nice articulation of what the main ideas are that the students should walk away with. So we do a unit on matter. We want to understand how the types and arrangements of atoms and molecules give rise to the fact that I can walk through this air here, that I can't put my hand through this desk, that I can put my finger into water, that I can stretch things, bend things, etc. We then go to change and talk about how matter can interact with other forms of matter and make new substances. We talk about energy, and we end with light and how shining light on matter can reveal its underlying structure. So that's the general organization, but then in addition, we think about the lesson design. Now, I've got a bunch of studies down here flipped classroom is the last of these because it really goes all the way back to the 1960s when Robert Karplus suggested, the learning cycle, suggested that you don't start by talking at people, you start by giving them experiences and then help them build an understanding based on those experiences. There are many great manifestations of this: predict, observe, explain. BSCS has this 5E model. Ricky and Tien have a model: observe, reflect, explain. And I just listed it in kind of an order where I want to get you interested. I want to help you observe and look at data, do experiments, analysis to build your understanding. Then we want to explain what we understand, what models do we have in mind, and then ultimately we'll want to assess, not to give you a grade, but to let me know and you know what the learning outcomes have been. All right, so we've designed lessons this way. And so I'm going to end with a simple example from a high school chemistry curriculum that I've designed, just so that you can get a flavor of how you can pull all this together to a different type of classroom, a different type of structure. Notice I'm still including a lot of chemistry here that builds to deeper understanding. So I have a high school chemistry curriculum that's now being published by Bedford Freeman Worth. It's in use in quite a number of high schools. It's really aligned with the national next generation science standards. It's called Living by Chemistry. We talked earlier about how life provides really good examples. And this is the second unit on molecular structure and properties. And it asks the question of the students, how does the nose know? And it's using now smell, which the students have a lot of experience with. They have a lot to say about. They have a lot of curiosity about, actually, because they're high school students. Duh. We did need to teach them proper words to use for some of the smells, as you'll see in a moment. All right, so this is just very quick, just 3 slides to give you a flavor of what this 5-week unit is trying to do over time. First day, I give you 5 vials. They each have a cotton ball in it. They each have some drops of a fragrance on them. And you get to smell them, and you get to classify them. And what you would find, the students actually do this, A and E are minty, B is fishy, and C and D are sweet. Now, we've limited the vocabulary so that we could start to have, that's one thing we point out, scientists make up words. All right, so that we have a common language, so that we can talk to one another. And so we've chosen those words because there aren't really good words for the sense of smell. So the students then say, what are they? Hey, bubble gum or whatever. So we then show them this. Now, this is early. They haven't seen molecular formulas and chemical names. And when we ask teachers to list these 8 patterns, they go, what are you talking about? The students can find 20 patterns. So do you see any? Limited data, but do you see any patterns? So which ones are minty? Oh, more than C8 is minty. It's exactly what they say. Okay, what else? Oh, N is a fishy element, right? What else do you see? 2 oxygens seem to make sweet, and 1 oxygen. What about the names? Own, 8, teens. All right, look at some of the numbers here. 10, 18, 7, 14, 8, 16, 8, 11, 10, 14. They'll notice this. Look at this. You know why that is, but that's the only one that's odd. All right? And so you can just go on and on with patterns. And by the way, what's the big one that jumps out at you? Carbon and hydrogen. Okay? All right. So then they've made a hypothesis. And now I'm going to give you some new ones. There they are, F, G, and H. How do you think they smell? Well, they must be sweet. And what's even worse, look at these 2. So some student will go, you made a mistake. So we let them smell them, but that's where we had to teach them a word. It's called putrid. And no other word is allowed to be used. Okay, and this then leads to, so how in the world can these two have the same formula and be different? I've got this experience. How are they different? So we get into how they link together. We look at functional groups. I'm not teaching functional groups. They all learn them because they think it's kind of cool. But that's not what we're trying to learn. We're just trying to learn about molecules, and that molecules fly through the air and can get into your nose and can bind to receptor sites. And by the way, if the air is clean, you can't smell it because the molecules in the air are not polar. So we have a lot of links to the world around them. And this unit goes on and looks at shapes as well, via CPR, et cetera. But, so you can see how by turning it around, by offering them data, it leads to a really interesting experience. In this case, we've got high school students who normally would not be engaged, much more engaged in learning chemistry. So to end, I would argue that we need to do research-based redesign for undergraduate chemistry. I think it begins with the assessments. They have to promote understanding as opposed to memorization, or we're really not getting to where we want to be. Use students' ideas and experiences to build knowledge. Let them observe. Step back. Let them explore the data, and you'll be amazed at what ideas they do come up with. And the context, the data, observations help to situate the learning. Smell is a good example because the students can really relate to that. By the way, some of the other units, the first one's alchemy. Can you turn a penny into gold? You wouldn't eat, and it's the kid with the hat in the back. You didn't do that, because if you did, you'd be rich. So, and they're trying to be smart about it, and you go, that's a great observation. Isn't that a great observation? That's a great observation. Because I would if I could. Anyway, and we have one on fire. It's really funny to watch high school students to try to make glass burn. So they think that matches, we can light everything on fire. And it's like, darn, the salt doesn't do anything. Okay, and I just want to end by giving special thanks to the NSF, because since the Chem initiatives, I really credit NSF for really stimulating all the efforts that you've heard about so far at this meeting. So thank you very much.